The idea of an electric field is one that's very important to electromagnetism and physics in general. Um, in our current scientific theories, most of them are what we call field theories. They say that any force or any interaction between particles happens through some kind of field. So the electric field is the vehicle, I guess you could say, for carrying the electric force. Although vehicle sounds like there's an object, but electric field is not an object, it's something that extends through all of space. It might be really small in some places, but there is an electric field through all of space. And it's kind of like a measurement of what the force would be if you put a small positive charge there. And gravity is the same way. You can think of it as a gravitational field. There's a field and then whatever mass is put there, and then you can figure out what force would be on the mass based on the field that is present at that location. So electric field is E. It is a vector, and so it is the force that would be on a small positive test charge. So we can say that our electric force is equal to a charge times the electric field, and we know electric force is K, and if the charge in question is Q naught, it's K Q naught times Q over R squared. So you can see that our electric field, this is for a point charge, or a charged sphere. Things get more complicated when they're discrete objects, but the electric field is just KQ over R squared. Very similar to what the force is. And since the electric field is force divided by Q, force is newtons, so electric field, our unit, is typically newtons per coulomb. Right? And keep in mind that since force is Q times E, and the charges tend to come on the order of 10 to the minus 6, electric field numbers tend to be very large. It'll be something like 10 to the 5th, 10 to the 7th, somewhere in that ballpark. Because the charges that are around are usually pretty small. And so for a reasonable value of force, you'll typically have electric fields that are pretty darn large. All right. So if you know the field, you just multiply by the charge to get force. And as I said, for a point charge, this is the electric field. So there are a couple different things. I could say, hey, there's some field in space pointing to the right that has a strength of so many newtons per coulomb, and then you put a charge there, and what's the force? It's a simple multiplication problem. And this equation also takes care of direction. If you put a positive charge in, then the force will be in the same direction as the electric field. If you put a negative charge in, the force will be in the opposite direction as the electric field. Right? Electric fields, we'll talk more about this next time because we're going to talk about drawing electric fields. But electric fields always point away from positive charges. So if you have a positive charge, the electric field, we tend to draw it using lines like so, but it will point away from that charge in all directions. I can make an infinite number of these lines if I wanted to. And then by analogy, they tend to point toward negative charges. So remember, the direction of the electric field is the direction a positive charge would move if it was dropped in that field. So if you put a positive charge here, it would be repelled from this positive charge, and so it would move along this field line. Likewise, if you put a positive charge here, it would move along this field and be attracted to the negative charge, and so it would move along this line. And the opposite if you placed a negative charge in either of those locations. Yep. So let's think about some things here. Take a conceptual problem. Let's say that we have charges in a square. They're all, and I'm just going to make little pluses. we'll say they are all equal magnitude. And I want to know what is the E field at the center of the square. Okay. Now, keep in mind, electric field exists through all of space. So there doesn't need to be any object at the point where we're considering the electric field. What is the E field at the center of the square? Well, we can just think about this point and think, oh, E field points away from positive charges. So this one's going to add some E field going this way. This one's going to add some E field going this way. This one's going to add some E field going this way. This one's going to add some E field going this way. They're all going to be equal. So that electric field is 0. We could also recognize that if we dropped a charge in the middle here, there would be forces, equal forces, that would all cancel out. Okay. Another question is what we can consider what is the E field is at the midpoint of the right side. Or we could do any side. So now we're looking at this point right here, thinking about what's going to happen there. Well, again, E field always points away from positive charges, so it'll point down from this guy, it'll point up from this guy will point up right, this one will point down right, but these two will cancel, and the y components of these two guys will cancel. This one's up, this one's down, and they're at the same angle, same magnitude, and so all that will be left will be some field to the right. Right? We can do similar things by arranging different charges. Let's say we have an arrangement like this: positive, positive, negative, negative, all in a square. What's the E field at the center of this one? And again, as I ask these questions, I think it would be a good idea to pause and think about it and figure out what you think it should be, and then double check. So E field at the center, what's going on there? Well, this would cause an E field going away from it. A negative would cause an E field going toward it. Negative E field toward it, positive E field away from it. And so these two each cause a field that's going down left. These two each cause a field that's going down right. So the X components will cancel out, the Y components will add, and we'll get a net E field pointing downward. And we can do that at any point on the square. All right, now let's say we have two charges. Q1, 3.6 microcoulombs. Q2 is 1.2 microcoulombs. Oh, negative, sorry. I meant to make that negative. 1.2 microcoulombs. All right. 1.2 microcoulombs. Why is that so blurry? All right. And let's say I want to find the E field. Let's call this x equals 0, where this positive charge is. We want to find the E field at x equals 0.22 centimeters. The electric field is a vector, so it adds vector-like. So from this guy, the E field from 1 is just going to be k times Q1, 3.6 times 10 to the minus 6 over r squared, 0.22 centimeters. That's 0.0022 squared. And that's going to be pointing away from this. At some point out here, this is going to be pointing to the right. The negative guy, well, the electric field points toward negative charges, so that field is going to be to the left, so that'll be a minus k Q2, 1.2 times 10 to the minus 6 over r squared. Well, this would be 0.05 centimeters apart, so that's 0.05, so we move the decimal 2 times, 0.0005 squared. Okay. Keep in mind, just like with Coulomb's law, we just plug in positive values into this formula and then assign the sign based on what direction we know the field ought to be. And I can punch that in my calculator. We have k k times 3.6 e negative 6 divided by 0.0022 squared minus k times 1.2 e negative 6 over 0.0005 squared. And we get, oh, that's huge. Well, that's what I get for just making up numbers. We get an electric field of minus 3.646 times 10 to the 10th newtons per coulomb. Right? That's how we can do an electric field when there are multiple sources. We could also ask a question like, where is the electric field 0? Okay. Now that this one may not have a point where the electric field is 0 actually, but in between them, electric field points away from positive charges and toward negative charges. So in between them, the electric field from this guy is going to be to the right. The electric field from this guy will also be to the right. So it can't be, the electric field can't be 0 in between them. Okay. Over here, the electric field from the positive guy is going to be to the left because it's away from the positive charge. Electric field from the negative will be toward the negative charge, that's to the right. So those are in opposite directions, but this one is a bigger charge and it's going to be, and it will always be a shorter distance to a point out here. So even though they're in opposite directions, the field from this guy will always be larger, therefore it can't be 0 anywhere out here. Over here, the electric field could possibly be 0 because this is a smaller charge and it's a shorter distance. So the E field will be larger because of the shorter distance, but smaller because of the smaller charge. Now, I don't actually know if the E field is 0 at any point, but we can check that out. It could be 0 out here. So we can call, let's say the distance, we said this is x equals 0, so we'll call this position x. So the electric field at some point out here is going to be k times 3.6 times 10 to the minus 6 over x squared minus k times 1.2 times 10 to the minus 6 over, and if this is x, then the distance from Q2 will be x minus at 0.17 centimeters. And that's squared. And I'm going to leave it as 0.17, and when I get an answer, it'll just be in centimeters. And I want to see where the E field is 0, so we set this equal to 0, and solve for x. I do some algebra. I can cancel out my k's, cancel out my 10 to the minus 6's, move this over and cross multiply. That leaves me with 3.6 times x minus 0.17 squared equal to 1.2 times x squared. And at this point, I'm just going to collect everything on one side and punch it into my calculator. When I do that, I get one solution of 0.107 and a second solution of 0.402. So since I set my x equals 0 here, 0.107 is in between the two charges, and this equation is only valid for out to the right of here because they would both of these would be positive if we were at a point in between them. So this one doesn't work. So when at x equals 0.402 centimeters, we do have a place where the electric field is 0. And going back to our original equation, that force is equal to Q times electric field. That place will be the point where if you place another charge there, there will be 0 net force acting on that charge.